So, how many branches are there on the tree of life? This is a representation of the periodic table of the elements that has been colored to show how the elements derive from astrophysical processes. And it's interesting to note that many of the elements can be formed by more than one astrophysical process. So that is to say, there's more than one astrophysical process pathway to the formation of some of the elements. And elements exist in all kinds of different abundances, and the astronomers who study star clusters have been able to show that when a supernova in a cluster triggers the formation of stars after the supernova, that the distinctive isotopes of the elements in the supernova are represented in the stars and the planets or the protoplanetary disks of the subsequent star clusters. So there's already a distinctive elemental structure that is pluralistic at the very start here. What happened here? Sorry about that. And that's not the whole story, because there are also the transuranic elements that were first discovered in the laboratory, and later some of them were discovered in very small instances in nature. And there's a hypothesized island of stability of transuranic elements, which opens the interesting question of whether there might be astrophysical processes in the universe of which we're not familiar that produces transuranic elements. So there's already a great deal of plurality in the constituents of the elements at this stage of the game. So everything that we know in the world is built up of the elements, but it's not built up directly of the elements. It's mostly built up of chemical compounds. And there are astrophysical processes that create chemical processes that result in chemical processes even in deep space. So we know, for example, that the greatest mass of water in the observable universe is at 12 billion light years away. So there's lots of water in the universe. We also know that there are polycyclic aromatic hydrocarbons in deep space. And in fact, just last month, there were a whole series of papers released on the discovery of polycyclic aromatic hydrocarbons in a very cold region of space where stars had not yet formed. I think it was like about 10 Kelvin or something like that. So you start getting some rudimentary chemical complexity even in deep space. Now, here's an interesting quote from Lynn Margulis. To go from a bacterium to people is less of a step than to go from a mixture of amino acids to a bacterium. There's already several interesting things in this quote implicit, and that's that there are complex structures, and these complex structures can be arranged in levels of complexity. And we know that people are more complex than bacteria, and bacteria are much more complex than amino acids. There's also complex processes, but to get from amino acids to a bacterium or from a bacterium to people, you have to go through complex processes. And these complex structures and complex processes are integrated with each other because complex structures often result in complex processes, and complex processes can produce complex structures. So they go back and forth with each other. And there's a lot of cyclical processes that we can think of as structures in time that have come up repeatedly throughout the presentations of this conference. So there are wet-dry cycles, there are hot and cold cycles in the versions of theories of the origins of life that feature ultraviolet radiation. There's light chemistry and dark chemistry. And we see throughout almost all theories of the origins of life some kind of cyclical process that acts as a kind of pump to push greater chemical complexity. And that usually occurs in complex environments. So as we know, on the surface of a planet, we've got, if it's not tidally locked to its star, it has an orbital periodicity, it may have a seasonal periodicity, and many other periodicities that come into cyclical processes. So in terms of levels of complexity, the layout of of complexity that is due to David Christian, who's one of the better known writers in big history. Yesterday we had a sketch of big history from Lowell Gustafson gave a presentation. So if you saw that yesterday, this is what I'm referring to. And so David Christian identifies 8 levels of emergent complexity. It doesn't matter if you take a slightly different way of dividing up the history of the universe into emergent complexity, you'll still get pretty much the same result in terms of what I'm going to say next. So on the left of the bracket here, all of these emergent complexities are observed on cosmological scales. Any direction we look in the universe, we see the background cosmic microwave background radiation from the Big Bang. We see stars, we see galaxies, can see chemical elements, we can even see exoplanets now. So we know that level of complexity is represented throughout the universe. On the right side of the bracket here, the other forms of emergent complexity, such as life, collective learning, agriculture, and modern revolution. Again, these are David Christian's thresholds. You don't have to accept them, but these all are only observed on Earth so far. So we can see that what we can think of our peer emergent complexities are going to branch off from this point of what I call post-astrochemical complexity. Because like I said, we can observe astrochemical complexity at a rudimentary degree throughout the observable universe. And if other emergent complexities emerge from prior emergent complexities, they're going to emerge from this point forward on a cosmological scale. So to get to more complex chemical compounds beyond those that we observe on cosmological scales, it requires further processes that involve gravity, energy flows, volcanism or the rock cycle, the water cycle. And we can observe within our own solar system that volcanism or the rock cycle is not limited to the terrestrial biosphere, and you could have this kind of complexity without life. There's probably not life on Jupiter's moon Io, which is one of the most volcanically active places in the solar system, and it's not driven by plate tectonics. It's driven by the gravitational tidal forces from Jupiter, which are very significant, and Io is small, so it can easily be pressed and stretched by the gravity of Jupiter to create this large level of volcanism. We also know that there was a water cycle on Mars in the past, and so whether or not there was life on Mars, there certainly was water, and probably created higher levels of mineralogical complexity than places that don't have the water cycle. So on Earth, the geochemical cycles like the water cycle and the rock cycle have combined with biogeochemical cycles, the sulfur cycle, the nitrogen cycle, the phosphorus cycle, and the citric acid cycle, to create an environment of great complexity, which is our contemporary terrestrial biosphere, which is extremely complex. So not only does life emerge on Earth, but a number of emergent complexities supervene upon life. And for example, sensation supervenes upon life, consciousness supervenes upon sensation, technology and art both can supervene upon consciousness, and various types of civilization that have appeared supervene on all the preceding emergent complexities. Now, in regard to the particular complexity of life, we all know that there's no universally agreed upon definition of life. One of the most common approaches to defining life is just to give a number of properties. There are many such lists. The most common list of the properties of life is this list of 7 properties, but I've seen lists of 4, 5, 6, 7, 8, and 10 properties. But if we take this common list of 7 properties and we arrange it on a Venn diagram, we get 128 permutations of these properties. And I think of this as the parameter space of life. So all of these things that are not all 7, all these parts of the Venn diagram that are not all 7 properties, they're like life, but they're not exactly the full example of what we consider life on Earth. Uh, so there are spaces within the parameter space of life that are lifelike, but not necessarily fully life as we know it. But since we are human beings and we are highly anthropocentric and center everything on us, we look at what I've called post-astrochemical emergent complexity, all culminating in human life. And we think of future emergent complexities following after human life. So one of the most common SETI scenarios is post-biological intelligence that is has been built by biological agents. So we're still patterning our view of emergent complexity in the universe over our experience on Earth. But if we go back to this graphic that I had earlier where I showed the division between chemical complexities that can be observed on a cosmological scale and chemical complexities that can only be observed on Earth, we need to think of these in terms of the varieties of different emergence that can spring off of each level of emergent complexity. So we pay attention to life as we know it, but there could be other chemical complexities that follow. And then there is a sensation as we know it, but even within Earth, we know that there are different forms of sensation that have emerged from life. Sharks have electroreception, bees see into the ultraviolet, pit vipers see into the infrared, and some fishes have distinctive forms of proprioception. And if we think of consciousness or mind as emerging from our particular endowment of sensation, we know that even within just the scope of the human mind, that there are radically different worldviews, or Weltanschauungen if you prefer. And if there are minds or consciousness arising from other species within the terrestrial biosphere, their minds are to be, we should expect these minds to be very different than ours, at least noticeably different than ours. And it keeps going as we build emergent complexities. You know, mind and consciousness, like I implied in an earlier slide, results in further complexities that supervene upon mind. But since our anthropocentrism guides our thinking, we see only this one narrative stream from emergent complexity and chemical complexity up to ourselves and beyond. And we really need to see this in the context of all the other emergent complexities that are going on at the same time and springing off from other sources of emergent complexity, both locally in the universe. So we see this in the terrestrial biosphere in terms of biodiversity. And the world is very rich in biodiversity. That's one of the puzzles of evolution, is why there's so much biodiversity. But we can think of this in a larger context of the chemodiversity of the universe that takes its departure from post-astrochemical emergent complexities. So in emergent origins of life scenarios that we are based on, a familiar scenario of a smallish rocky planet in a circumstellar habitable zone, we sometimes divide up the planet into the hydrosphere, the water, the lithosphere, or the ground, and the atmosphere, or the air. And there are emergent complexity theories that address each of these three areas or three divisions of the planet. There is the idea that Alexander Oparin's Oparin Ocean. This is not widely defended at the present time, but he clearly defended the origins of life in the open ocean. The idea of the deep hot biosphere was introduced in order to defend the idea of an abiotic origin of oil, but that hasn't had legs under it, as it were, but it has been adopted by some people in the origins of life community as a likely origin point for life. And there are the idea of aerial biospheres. This was discussed a lot last year when phosphine was reported to have been discovered in the atmosphere of Venus. That's been discussed several times already at this conference. This is an older illustration from Carl Sagan and a co-author who argued that there could be life in the clouds of Jupiter. But even though there are theories that involve possible origins of life in each of these spheres, the most complex chemistry appears at the interfaces of these divisions of the planet, where there are also energy flows that are available. So in this quote from Darwin that's already been used several times at this conference, the idea of a warm little pond, we can think of the famous Miller-Urey experiment and its subsequent versions as a experimental implementation of many of the elements that Darwin mentioned in his warm little pond, where we've got the geosphere represented by the surface, we've got the atmosphere, and we've got water all represented there as elements in this origins of life scenario. There's also the hydrothermal vent theory of the origins of life. Once again, we've got interesting chemistry because we've got an interface between the geosphere and the hydrosphere. And this is the basis of Gunther Wachtauhausen's iron sulfur world, excuse me. And then, of course, there is geothermal fields as a potential origins of life location. Once again, this is an interface between the geosphere and the atmosphere, and also there's hot water available, as in the hot water, the hot springs origins of life theory that we heard about earlier in this conference. And there's a nuclear geyser theory of the origins of life that attempts to address some of the problems with the hydrothermal vent theory, because one of the major criticisms of the hydrothermal vent theory is there's no wet-dry cycle, and the nuclear geyser theory adds in cycles that are based on the naturally occurring fission reactor, which would have been more plentiful in the earlier periods of Earth history. So in these origins of life scenarios, we can also add in the cryosphere, because at some point in Earth's history, ice was there were multiple icehouse events, which may have there are forms of chemistry that take place only in cold conditions that may have been important in the origins of life. So we can take the same idea of interesting chemistry at interfaces and apply it to subsurface ocean planets like Enceladus and Europa and Ganymede, all of which probably have subsurface oceans. There may be interesting chemistry at the interfaces of the ice and the water, of the water and the geosphere, and the geosphere and the ice, and it could be driven by gravitational energy flows from the gravitational tidal forces, just like as we saw with the volcanism of Io. We can also apply this idea to smaller bodies in the solar system, like comets. They have gases, they have ice, they have dust and debris, they have water, and all with interesting chemical interfaces. Probably, not at the scale that we see on planets and moons, but we can't necessarily dismiss it, because we know there are interesting chemistry in comets. So as we know that there are many different theories of the origins of life. There's RNA world, there's a pre-RNA world, there's an RNA peptide world, there's the membrane first lipid world, there's a proteins first proteinoid world. And in fact, there's so many theories of the origins of life that they probably haven't all been realized on Earth. In fact, I assume that the wide assumption is that there was one origin of life by one mechanism. But I'm going to illustrate this by these two overlapping spheres, circles, a Venn diagram. So I'm going to call mechanisms for origins N, because that's for nature. And I'm going to call theories of the origins of life K for knowledge. And we can see that there could be instances where nature exceeds knowledge. So there might be natural processes of which we don't know anything, but which were responsible for the origins of life. Or there could be instances where knowledge exceeds nature, that we have by our own creativity come up with perfectly viable geochemical or biochemical pathways to life, but they just weren't in fact realized in terrestrial life. And then there's of course the overlapping instance where we get knowledge is approximately equal to nature, where we both know a theory and it was a mechanism. And all three of these could have been exemplified in Earth history. There could be theories we come up with no exemplification in history. There could be mechanisms of which we have no theory yet, and there could be mechanisms of which we do have a theory and do have knowledge. So in this well-known illustration of the three domains of life, the archaea, the bacteria, and the eukaryota, we see them all connected to a same root, as though there were one source of one mechanism by which they came about. But in a very simple scenario of more than one origins of life, there was a paper from 2010 that distinguished one pathway to bacteria and another pathway to archaea and eukarya. In a situation like this, there might be one mechanism that leads to bacteria and a distinct mechanism that leads to archaea and eukarya. Just earlier today, Rosanna Del Guido called this multiple root genesis. So that's what I'm talking about here, essentially. And there may be multiple, or there may be fewer, there may be less in terms of mechanisms that actually resulted in biochemistry that's represented in the contemporary biosphere. And so there may be multiple mechanisms, and there may be the order in which these mechanisms appear on a planet may influence, the kind of chemical complexity that follows from that point. So given the astrochemical boundary conditions that we see on a cosmological scale, what kind of emergent complexity might we see under alternative selection pressures? So I want to give a thought experiment that I intentionally formulated to try to present something that's very different from anything we're familiar with. So emergent complexity without life, without consciousness, without intelligence, without technology, without civilization, all of the things that we know on Earth. So start with the idea of chemical complexity in comets. One of the first explanations for the unusual light curve of Boyajian star was a swarm of comets. That explanation isn't widely held anymore, but there certainly could be planetary systems where there are a great many more comets than in our planetary system, so cometary chemistry might play a much larger role. So let's say we get interesting chemistry on comets and it's widely represented. And there was a paper that came out in 2019 about some researchers who created an artificial material that had locomotion behavior and apparently metabolism. So it's not life, but it's like life in some respects. So it represents one of those one of those points in the parameter space of life that I showed earlier with the Venn diagram of 7 different properties of life. So to say we have this cometary chemical complexity with some non-biological metabolism. And so here's another idea. Everybody's probably heard about what Abraham Loeb has had to say about Oumuamua. He's even written a book about this. It just came out in the past few months. They hypothesized, Bialy and Loeb hypothesized in this paper that if Oumuamua represents a new class of thin interstellar material, either produced naturally or yet through a yet unknown process in the interstellar medium or in protoplanetary disks, or is of an artificial origin. So Abraham Loeb focused on the artificial origin, but we can also take the neglected alternative of there being a naturally produced very thin membrane that could be used for locomotion in a microgravity environment. So we add this up to our list. And one more item here from an interesting paper widely cited from David Ropp in 1992, where he noted that he thought it was pretty much inevitable that we would eventually discover radio communication in our own terrestrial biosphere. We know bioelectricity is fairly widely represented in the biosphere. So there's several different pathways, biological pathways to bioelectricity. So we add that to our list here, and we have non-biological equivalent of bioelectricity plus a coordination of system-wide activity by radio signals, and we get a potentially universe-spanning emergent complexity that is not life, not conscious, not intelligent, it's not technology, and it's not civilization. So the reason I try to formulate this thought experiment is not to show how weird it is, but to try to point to the principle of mediocrity, that I'm not suggesting this is something really unusual. It's unusual from our point of view, but we think of this as our peer complexities, that is, other complexities in the universe that has also sprung from the same astrochemical roots as we spring. And so terrestrial emergent complexities may be mediocre in the sense of having many peers, but our peers might be something very different from life. They're post-astrochemical complexities, but they're not exactly like life. So once we have a set of post-astrochemical peers and we have it defined, we can define subsets of the peers, and probably it's going to define a bell curve. So if we take what I call a wide peer class of emergent complexity in the universe, right now we're on the left side of the highly endemic emergent complexity. We only know ourselves on Earth. Like I said, we can only observe our emergent complexities on Earth. And though we may, if our civilization develops and doesn't collapse, we may become a more average emergent complexity in the bump of the bell curve, or maybe we'll become a universe-spanning emergent complexity. But we don't know ultimately where we're going to be on this bell curve, and we don't know where other emergent complexities are going to be on this bell curve. So thank you very much.